Our goal is today to cover part 1 and part 2, and therefore our next lecture we can do the synapse with neurotransmitters. So we're going to deal with just neurons, what's a neuron, and neuroglia. They're both in the same family. And then the meat and potatoes of this section is the resting membrane potential. We're going to deal with the ions, the gradients, and then an action potential. And that's really the biggie that we're going to aspire to be comfortable with by the time we leave today. Neural tissue as a whole is made up of 2 types. There are neurons, those are nerve cells that conduct electricity, and there are neuroglia. And I like to think of that as more like the support staff. They have a lot of different jobs, neuroglia does, but they're not conducting electricity. They're not really the messengers, the wiring that's really sending the electrical impulse. So we're going to be bringing up neuroglia in a couple different contexts. Our primary focus is the neuron itself. So we will focus on that, but I wanted you to be aware of that. A neuron is going to have these various parts, and you're going to need to know the parts. The cell body, the dendrite, the axon, and I have a diagram that we'll go through. The neuroglia these are the other types. There's 4 I have listed here. They just kind of give their name. You don't need to know their names. It just gives you a sense of what they are. They are just in this neuroglia supportive type function. They have very specific roles, but because we really are spending time on the electrical conduction aspect, our focus is going to be on the neurons. So we'll just kind of leave this just so you see them as a list, but we're not even going to go through their names. Beautiful picture here of a neuron with lots of little dots around the neuroglia, just so you can see how they all coexist together, but the neurons are the primary structures that we're going to be focused on. The types of neurons that you want to be familiar with and that you will need to know, also the types of neurons I'm going to tell you about and how they're built and the shapes that we're going to go through in the next couple slides, is going to be very, very important when we tie this into how does this overlay with our spinal cord and the nerves. So this is one of the reasons why I jump around in the textbook, because once we teach nerves that goes to a muscle, so I have to put these 2 together, I also want you to see how does this anatomy of a single neuron relate to how nerves are going to and coming off of our spinal cord. So all of these there's a purpose to them, but this is, again, I have a reason for doing things, but it's a little unconventional, so it's not always following the textbook. So we have the 2 main neurons that we're really going to be dealing with. Sensory neurons, that's bringing sensory information like, ooh, that hurts, or that is hot, or that is cold. Just sensory information back to the spinal cord and up to the brain. So sensory neurons can also be known as afferent. You're going to want to make these as synonymous terms. Sensory, bringing information from your body to the brain. Motor neurons, meaning it's coming from the brain and it's going out to tell your body something. It could be voluntary or involuntary, but it's actually going to tell a gland to secrete, saliva because you smelled some yummy cinnamon rolls. Or to go to your heart to speed up because you're excited about those cinnamon rolls, or or to your legs to do squats because you're working out. Those are just motor neurons, but also known as efferent. Afferent is body to brain, and then the efferent, I always like to think, is coming down and exiting out the spinal cord. That's your motor or control. Interneurons are little connections between the 2, and they're going to be within the brain and spinal cord, this is a sensory neuron. Our focus at this point is really going to be a motor neuron. We're going to learn our neuron anatomy through this motor neuron, and interneurons are also going to have funky little shapes. As just a generic, this is a neuron, which means it's a nerve cell. So as far as a motor neuron, you're going to need to know all of these anatomical structures. So the cell body is going to be this portion within here. That's just the cell body, and you have this little green nucleus right in there. Then the next thing we're going to look at are dendrites. That's these little sprout out feelers, if you will, that's radiating out from the cell body. The importance of the dendrites is that they're going to be receiving information. Another neuron is going to be bringing in, synapsing onto these dendrites. So this is where incoming information is going into this neuron. Because the key important things with neurons, it's a one-way flow of information. Information is going to get in on one side and it's going to travel on out the other side. And it's going to travel down a single axon. So it's going to be this here. This particular axon has these little yellow things that look like hot dog buns. They are known as myelin sheaths and Schwann cells. We will deal with them later. You can just have it drawn as just a single long axon. The axon will end up in all these little tiny axon terminals that we remember as being the start of the synapse or the synaptic terminals. They've got lots of different names, synaptic boutons. They're what's going to be hovering over a muscle cell and release that neurotransmitter. So you can see it's going to branch out to several of them. And so those are the end branches of the axon. So here we go again. I have it where there's two neurons because I wanted you to notice that this second neuron here, you can see the end of the first one is actually going to synapse or connect with the dendrites of this one, bring information down, and it can either then give information to a third neuron or go straight like to a muscle. So you can see the information is going to actually flow down in that order. So we have the cell body. That's this area here. There's the cell body in that one. Dendrites radiate off the cell body. They're going to receive the signal. The axon is this single one coming down. This one also has the myelin sheaths on it. And then the synaptic terminals are the little endpoints that's going to actually release a neurotransmitter. Who can remember the neurotransmitter that we talked about in last lecture that is released onto a muscle cell to get it to activate? Acetylcholine, exactly. But we're going to learn the next lecture there's lots of different types. There could be serotonin, there could be dopamine. So there's other neurotransmitters in different places. So the neurotransmitters are just found in these tiny little ends. I want you to picture the word neuron means one cell. So here's a one cell or one nerve cell. But then we hear the word nerve. We got nerves. We have nerves that are traveling through our body. What a nerve is lots of axons bundled together. So if we were to look at the cadaver, open it up, say in the arm, we're going to see arteries, veins, and nerves. They usually travel together. So we open up a cadaver and we're going to see, like a nerve coming down here. We move the muscles aside and we lift. That's an artery, that's a vein, and oh, here's another thing that's a little more dense. That's a nerve. What it is a whole bunch of axons all bundled together. The cell body and dendrites, well, they're way back in the spinal cord. It's only these axons that are coming out that we're now seeing on a cadaver. And then finally, the axon terminals are way down at the tissue. So we're not going to see that with the naked eye. So in this slide, we can see a single nerve is loads and loads of these little bundles of axons, where we can see in this part, the individual cell bodies that they came from are housed in the spinal cord or brain. We have our brain, here's our brain, comes down, and our spinal cord, okay, there we go. There's my dendrites, nucleus. Here's our axon, kind of coming out to little different, synaptic boutons, from the axon. So if I draw, say, dendrites up here, so to do this in green, sort of surrounding that might be up in the brain. And then I'll draw in purple. Maybe it came down and it came out onto, say, a muscle. We have the axon terminals are sprouting off to a single muscle. And sometimes the cell bodies, probably more often, you've got the cell bodies here in the spinal cord, and then they'll have an axon that comes off and it might go to a different place. Here we got some axon terminals over here. That's what these are here in red.
So it doesn't always come from the brain?
It's going to come somewhere from the brain or spinal cord. So that's just known as the central nervous system. That is brain and spinal cord. Anything that comes off of it is known as the peripheral nervous system. So what I'm pointing out is, okay, there could be cell body up here, there could be cell body here, but they're always going to be within the brain and spinal cord, that part. The axons, well, they might still be in here. We still have axons there. But once it comes off the spinal cord, it's really only the axons coming off. And then it's the ends are going to go to the gland or say to your intestines to move food along or to the heart to make it speed up. But you're going to have hundreds and hundreds of axons coming off going to the body. And these guys are bundled together. So if you see a nerve in an arm or a leg or wherever you're going to see nerves, and with the probe, it'll be about as big as a pencil, some of the nerves. Sciatic nerves as big as your pinky. And so they can be quite large. And literally, if you cut through the nerve, that's what this picture is. You're going to see the ends of all of these axons that are coming out at you. So they're just many individual neurons have their axons together. So this is actually what it looks like. So you can see all these individual axons, and they all go back to their own mother cell body somewhere in the central nervous system. So when we say nerve, a nerve is just a bundle of axons, but a neuron is the whole cell, a single cell. But a nerve is like hundreds and thousands of axons from many different cells put together. Even within a single neuron, within a single nerve, these here are arteries and veins because it needs to get blood to them too because they're going out, they're away, they need to stay alive. So you're going to see these bundles of axons, but you're also going to see some arteries and veins. So that's what this picture. The reason why I have this here is the Schwann cells or the myelin, the hot dog buns. We're going to talk about, it's actually one of the neuroglia. So it's part of, so this is the point of it's not the neuron and not going to make up, it's not the neuron, it's just happening to be wrapping around the neuron. So it's still a support cell, but it itself is in the neuroglia territory. So just to bring that back to. Myelin, which is these hot dog buns, is made by Schwann cells. These Schwann cells, which is the cell here that makes a single one of these. So it's going to just wrap around the axon. And so we have this here, it's wrapped around. So you'd have, that's known as myelin, made by a single Schwann cell. And then you can have another one. And you would have another Schwann cell making myelin. So there's going to be multiple ones of those. Are you good? Because they're separate from the neuron. They're their own little thing. Does that help? Sort of? Okay.
So each one comes from a single cell.
Yes.
But there's multiple of them.
There could be lots of them, yes. So you can see all down a single axon. If you have a really long axon, say here's an axon that's coming off and it's going all the way down to your leg. That's a really long one. So we'll have loads of these. You might have one that's a shorter distance. So just however long the axon is. Later, we're going to see how it makes the electricity is going to come down this way. If you have a neuron with Schwann cells, the electricity goes faster. It also has the added benefit of when you have multiple neurons. So here, when you have an axon for one neuron and another axon, and they're all going to be going, they're bundled together in the same direction. But say you have multiple of them. What if my blue neuron is sending an electrical signal? We don't want it to inadvertently stimulate red guy, right? So these Schwann cells not only make the conduction of electricity faster, but it also helps to insulate and protect one neuron from activating its neighbor. So it's almost like a real handy rubber outer lining like you would have in any wires over there. It's this other, again, with the support cell, it's not itself, it's conducting the electricity. It might quicken the electricity. It's insulating it from its neighbors, and it serves as a guide. The gaps in between them is called the node. It's a node of Ranvier. And these are the axon, exposed axon between the myelin segments. Now, we also have, if we were to slice open, and I have a bucket of some brains in there that we'll bring in at some point and have a look. And when you slice open a brain, we're going to see that there's some white and gray matter. Bucket of brains. You know, it's always good to have one, especially on test day. You know. So notice if you slice your brain or a spinal cord, it's going to be gray matter and white matter. So that's sort of big picture stuff. Cut a slice of brain open, bam, you see these two different colors. Spinal cord, same thing. So I want to go back to the neurons. We need to know what it means. Say we have another cell body dendrite, and it might connect over here. I need to get my colors. Has its own little axons. And remember, it's a little axon terminal. And it might connect to another cell body dendrite. And it has an axon. It's going to come down. And actually, its axon terminal is going to come to that one. Can you guys see that? The white matter and gray matter are areas where white matter, think of as just the wiring. So white matter is just the axons. Gray matter is going to be where the synapse takes place, like where the end of one neuron and the start of the other one. So white matter is the wiring. The gray matter is where you have the end of one neuron and the start, say the dendrites, of a second, neuron going off. So gray matter is this synapse connection. The white matter is going to be the axons itself, the wires. So what would this picture be a representation of? White matter. It's a really cool MRI image that they have now, so the technology is amazing. So we can see really the connections going up. We can see it coming up the spinal cord, going out to the cerebellum. We'll learn about these in the next unit. But you can see coming up, the thalamus is the middle of the brain. It's really the director where things are going to go to your higher order thinking. So we can see this is really like the electricity, the bundles of axons going out within the brain. That's all going to be white matter. Those are just the tracks of wires. Where gray matter takes place is where all of a sudden it's connecting. Oh, now we got to release a neurotransmitter onto somebody else's dendrites and light up the next neuron. So that connection that's being made, that's the gray matter. So it's almost like that's where the business is taking place, if you want to think. So that's where the white and gray matter is all about. So back to our brain here on the board and back to the myelin. White matter is also called white matter because especially down through the spinal cord, myelin is white. So you see that again as part of the axons that contributes to the color of the white matter. But not all axons have myelin, so just know it's axons. But we'll just keep things simple. If there's a synapse taking place, it's gray matter. If it's just the axon and just the wires, it's white matter. So let's think of some test questions that I might ask you about this. I might say dendrites are found in white matter or gray matter? Gray matter. Axon terminals are found in white matter or gray matter? Gray matter. Axon term. Neurotransmitters are found in white matter or gray matter? Gray matter. So anything here at the end is a gray matter. Anything here at the start is also going to be gray matter, right? So it's just this is going to be white matter. So when I said axon terminals, it has the word axon in it, but terminal means the end. So axon terminals are these guys, but that's where a connection's about to get made, or a synapse. So that's gray matter. Now, what if we damage a neuron? And this is specific to peripheral neurons, not brain, not spinal cord, but out of your arm, you get a really bad cut and you cut a nerve. And a nerve is obviously lots of little neurons in there. But peripherally, we have a lot of myelin on them, thankfully. So this is the process of what happens. So say A, the top view here, we have, this will be our site of injury. So from the point of where a cut is made, it's partway through, we know that the cell body is going to be in the spinal cord somewhere. So it's just these axons that are coming out that could get some damage from a cut. So we have a cut. Anything from the cut on distally is going to get broken up. So we have from the spinal cord, and the first portion of the neuron is still going to be intact. The distal portion is going to be disintegrated. Our immune system is going to come in and clean it up. We can't really repair something until you clean up the mess. It's sort of like a tornado goes through a town. You can't rebuild the town until you clean up and get rid of all the damage that happened first. That's the same with peripheral nerves. So we're doing this cleanup here, and then the little nub, the remaining axon on the healthy side, starts to stimulate some growth factors, but the myelin Schwann cells in the area help to form the tunnel that the axon's aiming for. So the myelin helps guide the repair down, all the way down to where it's going to go and say to the muscle that it's going to connect to. So the myelin creates a tunnel, facilitates the growth, and the axon has its own regenerating factors that's going to cause it to grow, but it's going to go down through the myelin. Now the myelin is doing its best to get back where it was, but sometimes it's off target a little bit. So that's where you have your occupational therapist retraining people if they have had a severe damage to kind of reuse their limb, you know, move their fingers and reconnect brains, telling this muscle what to do. And oh, you overstimulated, made it too strong. And you know, whether you vary what light touch, strong touch, and things like that. So that's just retraining your brain pattern and reestablishing those connections. So the important thing, this is just more of a list. What's going to happen in terms of nerve damage and regrowth? The distal portion is going to die off. Number 2, we're going to clean it up. We're going to have macrophages. That's part of our white blood cells that we're going to learn about in the next class, 202. It's going to remove debris. This is one of the limiting factors in the central nervous system to regrow. We really don't let a lot of our white blood cells in there, so we don't do a very good job cleaning up the damage, and therefore we have a harder time to repair. The Schwann cells that are found more peripherally here actually form a path for new growth, and they are going to wrap around that axon. So kind of make it sort of like a little needle, and it's the axon's threading this needle as it goes along. And so it's just the axon acts like scaffolding. So this is really what the image shows. So here's another schematic here where we can see axon injury. We have the distal portion would normally die, but this is the limitations in the CNS being central nervous system, no macrophages to clear the debris. So therefore you end up with no more axon going. So you're not going to get that electrical conduction to continue down. So for part 1, the 2 types of neural tissue, a neuron and neuroglia, either conducting electricity here or you're some sort of support cell. The types of neurons, we have sensory, also known as afferent, excellent. Motor, also known as efferent. And then we have interneurons, they're just kind of in between ones. The anatomy of a neuron, and we're dealing with just a motor neuron, we would have cell body with the nucleus, dendrites radiating out, axon, and axon terminals where the neurotransmitters are found. Myelin formation, we make myelin on some neurons, not all, but some will have myelin made by a Schwann cell. The job of myelin is to make the conduction of electricity faster, as well as prevent you from inadvertently stimulating neighboring cells, so it insulates it. One of the reasons why it takes so long for human babies to walk is that they're still myelinating their distal axons to their legs. So it's taking a while for them to coordinate the impulse from their brain to stimulate and contract a specific muscle in time to hold them up. So they're coordinating that patterning out there. So that's part of the limitations. Myelin is also what is attacked by people's own immune systems if you have multiple sclerosis. People with multiple sclerosis have an immune system that says, oh, myelin, you have got to go. And it will like go and attack it. I had a student years ago who would talk about his wife. He was during class, she had episodes where she could walk just fine. And then other times, and she couldn't, her leg would, just wouldn't be there. Because if she had the myelin not there on a neuron going to her leg, the normal signal rate that you would stimulate to get the quadriceps to contract before you take your step doesn't get there in time because there's no myelin, so it was too slow, and so it contract. So she would always walk down the hallways with her hand against the wall just in case it gave out. And so that's where multiple sclerosis can be really hard to detect in some people because it's intermittent, because your Schwann cells remake it, and then your immune system breaks it down, and then you remake it. So it's working, not working. Nerve regeneration and limitations, distal end dies, axonal growth through Schwann cells is helpful, but it can also do it without it, but it can help the Schwann cells make it better. The key is you have chemicals that stimulate nerve growth, but you also cleaned up the damage. The limitations in the central nervous system is we don't have our growth stimulators, and our damage cleanup are not what they are peripherally, so that doesn't always work. On to part 2. Now this is the doozy, okay? Now we have the parts. We're gonna put some of these parts to action. This is where we're really gonna, do our mental gymnastics, lose our marbles. No, we're gonna nail this. So we're gonna start off with, I'm just gonna read this at the start. Ions that determine membrane potential. So we're gonna first talk about, we're gonna talk about sodium, potassium are the two main ones. There's chloride, there's calcium, magnesium, there's other ones out there, but we're just gonna stick with 2, sodium and potassium. And we're gonna figure out where they are, and we're gonna figure out that there are channels that they go through. Sometimes they're closed, sometimes they're open. So we need to know where they start so that when the channel's open, where are they gonna go? So that's what we're gonna do. So we're gonna kind of build this up. We're gonna talk about pumps. How do we put things back where they started to be? So we have pumps that fix things back after we open up channels and things get messed up. Pumps reestablish them back to normal. We have these potentials, graded potentials, the action potential, this is more voltage changes that are happening because sodium and potassium are moving around. And then we're gonna, at the end, do continuous versus saltatory propagation. And just to get ahead of myself, the saltatory propagation is this. When we talk about, these Schwann cells and the myelin makes it go faster, it's called saltatory propagation. That's all. It's like it's jumping from node to node. So let's start off easy. What is an ion? So an ion is a charged particle. So it's some sort of, it could be an atom, it could be a molecule. Sodium is going to be abbreviated as Na, it's a positive charge. Potassium, K, it's also a positive charge. Chloride, Cl, it's a negative charge. But we're just going to deal with sodium and potassium just to try to make life a little bit easier. But I want you to see from this here, they have the arrows denote their concentration gradient direction. That's kind of a mouthful. Look at the pink. Think of how many we have on this side. So it looks like we have 6 on this side, and we only have 3 on this side. So it's concentration gradient, meaning its inclination of where it would want to go is going to be this way, right? Because it wants to balance out. So everything we need to know, where is it stacked up more on which side, so that where does it want to go? So here, sodium is in blue. We can see it's more stacked up on this side. There's only 2 on the right side, so its concentration gradient is that direction. So we're going to be using the words concentration gradient, so I want you to feel comfortable with that. And sodium and potassium, will be actually opposite to each other. When we talk about an electrical signal, electricity comes off, and we can measure it by electrodes on the surface, whether it's through the heart or down someone's arm to a muscle, is anytime a charged particle, a sodium, moves. It's the moving that gives us electricity. It is the movement across that we detect as the current, giving off of, it's the current that's moving across. So we want to create an energy potential, like charge our battery. We want to keep our neurons so that they could send a signal. It's really important that we shove all the sodium out and all of the potassium in the cell as much as we can, keep them separate. And it's when we want electricity to go down, it's all of a sudden opening channels and then they're going across their concentration gradients. That's really where we're going to come with this. So at rest, a neuron, nerve cell, is going to have these charges separated. And because a single cell inside has a lot of proteins and cell stuff in there, it tends to be really negative. So if we have our dendrites, there's our little nucleus, we have our axon, and it's going off two little axon, terminals here. A lot of sodium out here, and we have some inside too, but more out, right? And we're going to have potassium. Going to be some of it out, a lot more in. Okay. But also, what's inside the cell, we're really not going to see them, are a lot of organelles that just make it more negative. So at rest, that's what we're going to start off with. A neuron that's not sending a signal anywhere, that's just normal. This normal, happy neuron at rest is going to be at a negative, they call it a resting membrane potential. So I'm going to draw a graph over here. We have here, so at like minus 70 millivolts, if we were to put a little probe in here, I got one little probe, like if I'm measuring the battery and I put one little probe at the positive end and put another little probe at the negative end, I could measure the voltage of the battery, right? The same thing here, I could stick a probe inside this neuron and stick a probe out here, and the difference between the two is going to be minus 70 with reference to the middle. The inside's always going to be negative. So it just means there's a difference of 70. So it just means it's minus 70 compared to outside. So in general, we have negative stuff inside, we have more potassium inside, we have more sodium outside. We have channels that are going to be on the cell membrane for sodium. So I've drawn those in blue. And we're also going to have some channels for potassium. Put those in because they don't share. A channel is made for one ion. So you have some for one type of ion, you have another for another type of ion. And then we have another funky thing. I'm going to do it as a circle, and this is a pump. So if a whole bunch of our sodium, so when the cell is at rest and really happy, and we have a lot of sodium outside, at some point, it's going to leak in. And some of these channels are leaky, and they kind of make their way in. And then the pump here just says, hey, kick you back out. So these are pumps. It's going to send it back to begin where it began. So it requires some energy because you're pushing it back against its concentration gradient, but it helps to keep these charges separate. I have the blue dots as sodium, and so you can see there's more blue outside of the cell compared to inside the cell. We still have some inside the cell. They're just more outside the cell. This is still negative membrane potential. We're at rest. We're minus 70. And this is just how the balance is. A lot of potassium inside the cell. You can see the pink dots inside. You have a lot more sodium out. In total, we have more sodium than we have potassium. If you think of a cell membrane as a wall, channels are like the doors. You can open it or you can close it. We have some channels that are opened if a chemical touches it. We have some channels that are opened if voltage. We have just different ways of getting that door to open. Think of it that way. Sometimes a chemical will do it, only chemical ones. Sometimes a voltage will do it. Pumps are gonna put things back where they ought to be if things get through the channels. And carriers are also involved, but we're gonna spend less time on carriers. So channels and pumps are our main focus. So in this case, we can see a lot of sodium outside the cell. We can see the cell membrane is made of a lipid bilayer. And the black lines represent channels that cross the membrane. So this is a closed channel. And this is an open channel. So you can think of it as like a little tunnel. Well, now one of those blue dots can go in. It's going to go down its concentration gradient. When given the chance, you can see, because we have so many outside, which is on top. So the ions are going to move what's known as down their concentration gradient. We can see that they're coming in this way. But when we want to get back to normal, we have a pump that's going to take our ions and with the energy, so we have to actually push against the concentration gradient. So it requires energy to do this. ATP comes in and the pump rotates around and lets our ions go back out. So in this schematic, we can see the channels are closed, the charges are separated. What do we have a lot of in the extracellular fluid? Sodium. What do we have a lot of in the intracellular fluid? Potassium. So they're separated, channels are closed. This is known as resting membrane potential because the charges are separated, that's the potential. We're gonna be at about minus 70 millivolts. This is the concentration gradient direction if we were to open channels, right? If we were to have a channel open, we could say the high amount of potassium inside would want to go out. If a sodium channel is open, the high amount of sodium would want to come in. This is their gradient direction. So when the channel opens, sodium is going to go in. Potassium opens, it's going to shoot out. So here's our pump. Pumps are going to take the sodium that snuck in, and it's going to take the potassium that's out. We're going to use a little energy and move it around, and then put them back where they came from. So now we're back to normal again. So of the channels that we're going through, they're going to be ion specific. There's sodium channels and there's potassium channels. They only let their own guy through. And they're gated for regulation, meaning sometimes we open them at certain times. This is where we have the chemical versus voltage coming in. So this is a little flap. So you can see there's a flap on the sodium channel and there's a flap on the potassium channel. Now they're closed and now they're open. Okay, so that's kind of how it works. You have a little gate. Whatever triggers the gate to open and close could be a couple different things. They could be voltage gated or chemically gated. Voltage gated channels are going to be along the axon. Chemically gated channels are here in the dendrites, on the surface of the dendrites, because they're channels, so they're on the membranes, but it's in the dendrite region. The voltage gated channels are along the membrane on the axon. Voltage gated channels that are here on the axon can be one of three ways. Here's a channel. It could be closed, okay, nothing's coming through. It could be open, now it's coming through. And then you close it again, they kind of go in a lockdown, like I need to wait a while till I'm ready to go again mode. So that's what closed and locked. So I like to call it locked. Your textbooks may not call it locked. But it really goes from I'm closed, I'm ready to roll, just give me the signal. That would be at resting membrane potential. You get some signal, it opens. And then when it finally reaches another signal, to close. But then it takes a while for it to reset. So there's a moment, few moments, that it's gonna kind of like not open again until it's like back. So that's the 3 phases. Yeah, but it's the same door. Say you go out, and when the door first closes, it locks for about 3 seconds before it's ready. Then it unlocks. So it's like a 3-second lock. You know, Adriana can't just go right behind you after the door closes. Like she could pull on it and it's still just closed. But then if she waits, just be patient and it'll open just fine. It's going to be closed, ready to open versus closed and needs to reset for a little bit. It's going to get in this lockdown mode for a few moments. Now a pump. Showed you a picture of the pump earlier. They're going to be, we have what's known as the specific name now for the pump. So you only have to know one, is known as the sodium potassium pump. We already know that it uses ATP to be powered because it's going to push everything against their concentration gradient to reestablish the concentration gradients. This will carry 3 sodium, because we have more sodium total than we do potassium. So 3 sodium for 2 potassium for each turn of the pump that you want to think of it as that. It maintains this resting membrane potential. Just kind of stuff's going to leak through, but as long as the pump's going, it's going to keep things fairly separated so that the cell can be at its really happy -70 resting mode. So here's a picture of the pumps. We've seen this earlier. We need energy. You notice there's 3 blue dots at sodium, 2 pink dots at potassium. They're going to rotate. So now we put sodium out to the side that already has lots of sodium. That's why we need energy to sort of push it against its concentration gradient. And then these ions will then go back to where they belong. So now we've got their separation. We've got a buildup of sodium outside. We have a buildup of potassium on the inside. So this is resting membrane potential. How do we change it? We know how we're maintaining it. So what do we do to change it? So here we are at the start. Again, we're starting with the redundant parts here. Sodium, lots of it outside. Potassium, a lot of it inside. Chloride is also outside, but we're not going to talk about chloride. There are negatively charged proteins inside the cell. The difference in charges between the outside compared to the outside of the cell is going to be around -70 millivolts. So again, just restating where we are. Inside the cell is more negative than the outside because it's got the separation of charges as well as negative proteins. Number 1, I have here negatively charged proteins inside. That's one reason why we're down at -70. Number 2, a huge amount of positively charged sodium is outside. So compared to the inside, that makes it also negative. The inside seem more negative. And although there's positive potassium inside, there is so much more potassium, sodium outside that the difference of the extra positive on the outside and the negative inside, that's where we get. My test question on this really is, what is the resting membrane potential? And it is -70. I'm just trying to give you a little more background so you understand why. A graded potential, this is like a blip on our voltage meter. What if something happened in a cell that we just opened up some sodium channels and we had a little bit of sodium make its way in? How would that make the inside of our cell? Is it going to make it more positive, more negative, or the same? We just had a bunch of positive ions, it's a sodium, come into the cell. So yeah, so the inside all of a sudden got a little more positive blip. So instead of it being at -70, if we had some sodium that came in here, we can see this kind of coming up. You're going to make it be less negative. If we're coming up this way, less negative, it's known as depolarization. That's depol. But what if, in this case, we were to open potassium channels and some of our potassium leaves the cell? How is that going to affect our cell here? Potential. So we're cruising along at -70. At -70, all of a sudden, something caused the potassium channels to open. Some potassium left. It was a positive and it left. How is that going to affect our cell that we're measuring here? So it's going to take it away. So all of a sudden it's going to bring it down because we lost some pluses, right? Does that help? So that is going, in this case, if this -70 is our baseline, then going further down is known as hyperpolarization. Sodium channels cause depolarization. Potassium channels will cause hyperpolarization and repolarization when we get to that point. Okay. So depolarization, becoming less negative, it's because of sodium. Notice our sodium channel opened. We're going to have some sodium ions that are making their way into the cell. And now we're at -50 just because it got more, it didn't become positive, it just became less negative, if you will. But it started to move up. That's depolarization. Same thing with hyperpolarization, but the other way. Sitting at -70, all of a sudden we open up a potassium channel. Some potassium is going to leave. And now we're like further down than we started again. So it just brings you further away or closer. That's what that is. So now let's recap where we are, because now we're going to do the action and we are bringing it all together. So let's just say we have an axon. We know what this neuron looks like. We know about channels. They're pretty specific to their own type of ion. We know that they're closed sometimes. We need a special signal to open it, a certain voltage or a chemical. We know the chemical ones are here. The voltage ones are here. We know that if something affects the voltage sodium channel, it's going to make the cell more positive. If we know something affects the potassium channel, it's going to make it more negative. And whatever, once the channel's open, our pump has to re-establish the gradient and putting things back where they started off at the rest. What we're talking about with this action potential is essentially the cell is at rest. Something's going to cause it to go positive. We know that's going to be because of sodium. There is a magic number, 55 millivolts. This is the magic number for our voltage. It's a magic number for our voltage-gated sodium channel to be open. Remember, it stays closed until a certain number. 55 tells it to open. What we did prior to this, when we talked about depolarization, we could have sodium let a little in, but if it just went to 60, then the body cell's like, whatever, a little bit came in, pump, bring it back. But if all of a sudden enough sodium had come in that we actually reached this 55, bam, those sodium channels are gonna go wide open. So we have like random little graded potentials that are happening all the time, but a full thought to create an action potential to make something happen is going to actually hit this 55. And then it becomes way more positive. We peak out, plus 30 is our peak, and then we're going to come back down, overshoot, and get back to rest again. That's an action potential, and that's what we're going to work on right now, is putting that together. But it all has to do with these channels, opening and closing at different times. Phases of an action potential is initial depolarizing signal. That's the 55 I have on the graph. It's known as threshold, like you reach this point. Depolarization is where you just rapidly is going to continue up because this threshold opened many, many more sodium channels. So we have now a flood of sodium coming in, getting more and more positive. But just like the voltage signal that said, hey, I hit 55, it's open, the same voltage signal at 30 says I'm closed and locked. I can't get any more positive than that, I've shut down. So those are the voltage variations, the open signal and the closed signal. So that's what's on here. And repolarization is coming back down to reset it, if you want to think of it that way. And there's this little undershoot loop that we're going to see when we see the graph again. So depolarization means we're becoming, we started with negative, we're becoming less negative. So 55 is still negative, but it's more positive than 70, right? So we're sort of moving up. Cell membrane voltage, once it reaches 55, we basically bumped up by 15 millivolts. Our sodium voltage gated channels open. Sodium rushes into the cell, it becomes positive. So in our picture here, we have our sodium channels here. And ultimately, let's sort of skip the initial. Let's say we got positive enough here that we reached this threshold. So the cell was here at minus 70 millivolts. This positive here, we went up, reached threshold. That's here, the plus. I'll make this plus here. At this point, this positive is sensed by this very first sodium channel because it's right next to it. It's the one, and because this one's a voltage gated one, it senses the 55 and therefore opens. It opens and a bunch of the sodium starts to come through, right? So this becomes positive. Well, then this next one senses it and it opens, and we have some that come down and it becomes positive. So you can see how it's doing it, and so that's what it means as a positive feedback loop. It's going to become positive, but it's opening more channels, the neighbor channel, and then the neighbor. It's like dominoes. So this being positive here won't affect the one here. It's affecting the neighbor, and then the neighbor, and the neighbor.
So it's like a chain reaction.
The chain reaction is the term for that is propagation. So we have this depolarizing that moves up. Now I want you to see, we know we're going to peak out at plus 30 and we have 0. So we are known as depolarizing. Depolarizing. But at 0 millivolts, those channels, those sodium voltage gated channels are starting to close. It's like you're driving in your car and we know we need to be at a full stop at some point. So when you put your brakes on, you're not like driving at 25 miles an hour and then 0, right? So just think of 0 as the brakes are getting put on, but you've reached a full stop because it's like you have this, you know, channels are open, and at 0, that's a signal to close the channels, but they are all completely closed because some still is making it in but at plus 30, everything is completely tightly locked down. We're good with that. So that's why I have on here at 0 millivolt sodium channels inactivate, but by plus 30, the peak, it goes to plus 30 because that's like you apply the brakes, but you come to a full stop at plus 30. So we're going to go all the way up here. So this here is sodium voltage channels are open and they are starting to, we'll say, closing. And at the top, we're going to say they are closed and locked. Remember, there's that brief locking moment. We don't want to open anymore. The cell says, plus 30 is plenty for me. I cannot get more positive than that. Okay. And that was here, sodium rushing in. So it became very positive. Sodium's rushing in. We are getting positive on the graph because a lot of pluses are coming inside our cell. So the cell is at plus 30 and not very happy about it. The cell says, I'm really comfortable at minus 70. How do I get back down there? What do I need to do to get back down there? What do we have a lot of inside? Perfect. We have a lot of potassium. So we've shut down, we're at plus 30. We've closed our sodium channels, but our potassium channels at plus 30, we're going to say closed and locked for sodium, but we're going to say open plus channel. Before I move on, that's why I want you to realize each channel is its own. Some channel, sodium, says at 55, I open. Potassium says 55 does nothing for me. Potassium just says at plus 30, I open. So each channel has its own trigger of what's going to open it and what's going to close it. So that's where, but they're all voltage gated channels because it's the level voltage that did it. So open potassium channel, that's happening at plus 30. When potassium opens, where is it going? We have a lot of it in the cell, so where's it going to go? It's going to go out of the cell, and because it's going out of the cell, we're losing positive, right? So positive is leaving, and we're actually allowing this to come back down, and that's what repolarization means, returning back down. Repolarization, the cell is becoming more negative. It actually is so overzealous in its shoot that it kind of passes our resting membrane. During this time, our sodium channels are still in lockdown mode. They are inactivated, they are closed and locked. Here is the overshoot. We actually passed our minus 70. It came down. We were able to, we hit minus 70. We were able to close our potassium channels. We have this sort of overshoot that takes place, that we're re-establishing things. All of a sudden we have to kick all the sodium out that came in. We have to bring back the potassium that went out. So we're rebalancing it. Do you remember what part rebalances it? That's this undershoot or overshoot, either way. But what is fixing the gradients? The pump. So this is where that sodium potassium pump is churning around, using a lot of energy, kicking the sodium back out, bringing the potassium back in. That's this green part. And then when we're done, it's back to its resting membrane potential at minus 70 again. This picture has everything we just did. We're at rest, the cell's happy at minus 70. These little lines represent a graded potential. Like, all right, something made it a little positive, this one made it a little more positive, but it just went back to normal. It didn't reach the threshold. But something really caused it to surge up, and as soon as it hit this threshold, those voltage gated channels came wide open. So we had a flood of additional sodium that came in, causing that graph to shoot. Those sodium channels locked up, potassium channels open, so we were able to come back down. We have that overshoot or undershoot, we're repumping, reestablishing our gradient, and it's back to normal again. So remember our neuron that we drew here, and we had kind of little ends coming off here. The marker's failing me. Nucleus. When we talk about an action potential, say we're measuring this voltage, it's going to happen, say, in this part. So we get really positive, then we get negative again, we do this whole thing. And then it happens to this part, and then it happens. So it's like we're measuring this graph here one moment in time, like at one part. But we know it's going to happen then to this next part and the next part, and that's the sort of propagation or chain reaction that goes until finally we get to the end. And at the end, do you remember what was hidden inside of our axon terminals? Neurotransmitters. Ultimately, we have this action potential is this electricity that's traveling down, causing ultimately these neurotransmitters to get released out the ends. So here we go. A, resting membrane potential. So that's minus 70. Minus 55 is our threshold. Sodium voltage gated channels open. We are depolarizing, and we can see sodium is entering the cell. That is C. At 0, we start to close our sodium channels. At the top, at plus 30, our sodium voltage gated channels are finally closed, and now they're locked. It's known as refractory. But we also, at the same moment, open potassium channels. Potassium exits the cell, causing it to go down to be more negative. That's called repolarization. We get to that. Now we start the relative refractory period. We haven't talked about the refractory periods yet, so I just have it here if your notes are complete, but we'll do that in a moment. We actually get this whole hyperpolarization or overshoot or undershoot. The sodium-potassium pump is doing its job in this phase, and we finally get back to normal again, and we can start over. So a new stimulus can actually come again to the nerve. So remember when I said I had to make a thought to go to my arm and it twitches? Well, what if I just want to hold on to something? That means the nerve doing it and the nerve doing it over and over again. So once this depolarizes, this is depolarizing, now this is recovered again. And now we can actually have a follow-up action potential coming behind it. This is just another way to put it. The initial signal here is really a graded potential that was just big enough to reach threshold. Then we have depolarization, sodium's entering, repolarization, potassium is exiting, the overshoot, rebalancing. The refractory story, it's a sodium channel being locked. When it is locked, you cannot have a second action potential coming along. And that means you're an absolute refractory, meaning you can stimulate the nerve again, but it is dead to the world. It says, I am peaked out. You cannot make me open my sodium channel again. It is locked. But when we come down, we start the green. The cell says, you know what, I'm still not ready. I am not ready to go again, but I am back to negative. So if I get a bigger than normal signal, I can go again if I have to. So that's what the relative refractory means. It's still in recovery, but it can if asked by a larger signal, essentially. But you finally get back to where it's blue here again, and the cell's like, hey, I'm done with refractory. I'm just ready to go. Extra push here, the relative, or there's no way, Jose, right here. That's the absolute. Propagation down an axon, the whole nerve. Now we know the nitty gritty of what's happening across the membrane. Channels are opening, channels are closing, sodium's in, potassium's out. This is what we already did, really. This continuous one says, hey, if I depolarize this first part, it's going to stimulate the next part, and it's going to depolarize, and it's going to stimulate the next part, it's going to depolarize, and so on. And so while we're depolarizing over here, way back at the beginning is already recovering. Continuous propagation in this guy just means one section of the axon does it, causes the next section, causes it again, like dominoes. Saltatory propagation means we could do faster because now we have myelin. The myelin is now across here. It's wrapped around this axon. Let me redraw our axon here. We have more myelin, so we can't see the axon through it. So saltatory propagation is where we have depolarization taking place here. And instead of saying, oh, this channel and this channel, say there's, it just beams across and actually stimulates that one. So it's like it makes this part positive. It beams it through. You get to skip a whole bunch of channels opening and closing. And so it makes this one happen and this one happen. So you can see how it's a lot quicker and takes less energy. So that's saltatory, and those ones are myelinated axons. Who can remember what these gaps are called? Nodes of? Yep, of Ranvier. So depolarization and repolarization, this whole action potential thing, only happens in these node sections. There is a test question that will ask you, tell me about continuous propagation and saltatory propagation. So here is continuous propagation. We can see where we're depolarizing each little segment at a time as it goes down the axon. But if we have a myelinated axon like this guy, we can see where we depolarize only in this node section. So it's quicker and more efficient. So let's recap. Ions that determine membrane potential. Which ones were we talking about today? Sodium and potassium. Where is there a lot of sodium? Outside of the cell. Where is there a lot of potassium? Inside the cell. If we want to make the cell more positive, what happens? If we want to make the cell more positive, sodium. It's going to open and sodium enters. If we want to make it negative, potassium leaves. Types and activation of channels. So what type of channels do we have? So the one we talked about are voltage gated channels. The certain voltages are going to open and the certain voltages are going to close. There's going to be different for each one. So we know sodium's voltage is open at 55, completely shut down at plus 30, lock to reset until it gets back to minus 70. But if the cell's still not balanced, it'll take more than the 55 to open it back up, in terms of stimulus. Once you get back to resting, it'll be. So that's the refractory story. Potassium is open at 30, close at minus 70. We also mentioned, but we'll talk about when we talk about the synapse more, the chemically gated channels. But I still want you to know chemically gated channels are going to be in the dendrites. Voltage gated channels are on the axon. Membrane pumps, after our channel's open and ions are moving across their concentration gradient, when they do this whole action potential thing, we need to reset and start over again. If we didn't have our pumps, we'd have one stimulus of our nerve down, we would have no energy to reset, and we would be dead. Or that was what happens in death, essentially. We're a dead battery, is really what we are. So membrane pumps, sodium, potassium, ATPase pump, 3 sodium and 2 potassium get turned. Graded potentials means something happened to a nerve to cause it to be a little more positive. If the graded potential was big enough to hit 55, it's going to cause an action potential. If it was little enough, it'll just be positive and go back down. The action potential diagram, you're going to need to know the phases. What's the voltage for resting membrane potential? What voltage is for threshold? That determines opening the sodium voltage gated channels. Depolarization going up is the result of sodium influx into the cell, peaks out at plus 30. Sodium is shut down, but potassium opens. We now enter the repolarization phase. Potassium is leaving the cell. It shuts down. Now, we have too much sodium in and we have some of our potassium out. So that undershoot or hyperpolarization or overshoot, it's got lots of names, is that pump fixing things. And then we come out the end of it back to resting membrane potential again. So that's a diagram. The refractory period just means what's going on with your sodium channels. We hit 30 and we are in lockdown mode. Absolute means absolutely not, it won't open again. It gets to minus 70, all right. Still things aren't back to normal, but relative refractory, it could open if it really needed to. You make it through the undershoot, we're back to just normal close, just ready and waiting. Okay. Continuous versus saltatory. Continuous is the slow. One section stimulates the next section, stimulates the next section, and it's just kind of goes along like tapping the individual keys on a piano. Saltatory propagation is our speed up one. And what do we need on an axon to make saltatory propagation happen? Myelin sheaths. Yeah, made by Schwann cells. When you have axons that have myelin sheaths, we zip an action potential from start to finish very, very quickly. Okay. Kind of wanted to set it up a little bit better. Here's the dendrites and cell body. So we're just going to, here's an axon from a neuron with an axon terminal. What can we find in an axon terminal? Neurotransmitters, perfect. So have like little vesicles, remember, and there, I'll make these little dots in there. Yeah, well, it could be lots of, we'll learn about other ones, but the one we know. So the red dots are representing a neurotransmitter, and it would be going to another neuron here. I'm going to make the axon of this one a little wider, and this is, I just made that one to have one little ending. It can go lots of different places. So what I wanted you to know is we'll stick with our color coding where we had blue for sodium. We have, this would be a sodium channel, our blue sodium channel, and we're gonna have a sodium channel, several of them here down the axon. As we go over, we have several of them on the surface of these dendrites. The difference that I want to point out is that the ones on the dendrites, whether it's sodium or I wrote it with a red pen and it was potassium, because another neuron would be coming down and sending out the little neurotransmitters, the fact that the little neurotransmitters would bind to it to cause it to open would make this what kind of gated channel? So it would be a chemically gated channel. So it could be, so it just, the neurotransmitter is a chemical. Well, is a chemical. And so the fact that we let a chemical out to bind to a channel, and then the channel opens, and we already know sodium is outside of the cell, so sodium enters the cell. But the fact that the trigger to open that channel was because a chemical bound to it. And then later, we're going to learn today about the chemical popping off, and then now the channel will be closed. So the channel is just really going to be open or closed, depending on whether a chemical has bound to it. On muscles, if it's a muscle cell and not a dendrite, it would specifically be acetylcholine. In the brain, we're going to learn today about the different types of neurotransmitters. It could be lots of different ones. We could call the chemical dopamine or serotonin or norepinephrine or glutamate. But the bottom line is it's a chemical that bound to it, and that's what was the cause it to open. So I wanted just to be clear that the chemically gated channel is the only place on a neuron that would even be getting chemicals are going to be the dendrites. So that's why they would be there. Because the chemicals are being released by the axon terminal of another neuron, of the preceding neuron, and then this receiving neuron that we're going to be measuring from is receiving the chemical, but the only receiving place from the neuron is their dendrites. It's the starting point for a neuron, where the axon terminal is the end point. So we're getting the end of one neuron and the start of another. Before I talk about the voltage-gated channels, who remembers in nervous tissue, central nervous system, gray matter, white matter, what would be this part here where we have a cell body, dendrites? That is the gray matter. So anytime we're going to learn about gray matter, and we're going to do the spinal cord in another lecture, in the next unit we're going to do the brain, just know that the gray matter sections are where we're actually connecting from one neuron to the next one. So there's, but that's where this connection is taking. And so white matter would be mostly made up of what? The axons here. They're more like the wiring to take it to another part of the brain, where then it would connect to another neuron. So I wanted to make that, those areas distinctive. The other point I wanted to make over here are, if we, remember we talked about voltage gated channels. So I'll put here voltage gated channels. They will be on the axon. For sodium specifically, so I'm just going to say, put the Na up here. What voltage would cause those channels to open? Minus 55 millivolts, because that's known as threshold. What voltage will they be completely closed? And remember, these channels, when they close, there's a locking lag. Yes. They're going to be closed, and we'll just say end locked at plus 30 millivolts. So the point here is voltage gated channels will have a specific voltage. Really depends on how the environment of inside the cell is getting positive or negative. The level of this positive or negative state determines on whether the channel is going to be opened or closed. Not a chemical over here. So that's what's happening here. To be complete, let's then put the same voltages for the potassium channels. So if we say the potassium channels, what would cause them to open? What would be voltage that because they've been closed, and what voltage would we have to get to?
Plus 30.
Positive 30, exactly. And at what point would they close again? Minus 70, exactly. Okay, so I really just wanted to double back with you guys and not only remind you of the neuron anatomy, where we're going to find chemically gated channels and why, because that's the place of the neuron that's going to be receiving chemicals. And then where we will find voltage gated channels, and then in a voltage gated channel, at what point, just because you have a voltage gated channel doesn't mean that every channel has the same voltage. It's going to have their own independent value that's going to cause it to open and close. Are we more comfortable about those elements? Who remembers what will actually reestablish the gradient? Once we open these channels and our sodium and potassium are moving, and then we're done with the action potential that we're about to draw, how do we get back to normal again?
Reset.
Yes, it's a sodium ATP, sodium potassium ATP pump is the name of it. And how many sodiums are transported and how many potassium are transported for each molecule of ATP? There will be 3 sodiums and 2 potassiums that will be transported for every molecule of energy. Okay, so you have all the elements. Now we will just go rehash the actual action potential graph. Here's the graph of the action potential. We are at rest, if we're measuring a neuron, we're seeing what the voltage is. What is the voltage at rest? And what is this called?
Minus 70 resting place.
Minus 70 millivolts. And this is known as the resting membrane potential. I'm going to draw this again. I'm drawing 2 neurons again. How we start, we talked about this whole thing about graded potentials the other day, and I didn't want to be too much in the weeds with graded potentials. I just wanted to be aware that there can be blips that go up and down. How we achieve an actual action potential, who can recall what the voltage needs to be in a neuron for us to actually activate our voltage gated channels on the axon? So we need to get to minus 55 millivolts, and I'm just going to put a dotted line because it's not really where the cell is at. So this sort of is, so we're going to, and what is this level called?
Threshold.
So it'll be the threshold. How we get to a threshold, if we want to get this neuron to make an action potential, what will happen is this neuron is going to stimulate it. So it releases its neurotransmitters onto, and usually several neurons are serving, or this one has several ends that might be going to it. Other little areas here. And so these little squares I'm drawing are sodium channels because they're here, and when they're going to react to the chemical or the neurotransmitter, we know they're sodium chemically gated channels. So if enough of these cause sodium to enter, we have a lot of sodium to enter, this whole, we want to think of this part of the neuron as just kind of one cumulative whole. And so if so much sodium comes in that we get really really positive. So we can see that as all of a sudden the cell, and we're measuring really from the start of the axon here, we can see this neuron's getting more and more positive from this influx of sodium from another neuron stimulated. So enough actually went in that it became positive enough that the first adjacent, I'm just going to put a little V. So we know the blue means it's sodium. So I'm just going to put a V because we know that one's a voltage gated channel. It's on the axon. It's sitting there. The environment around it had been minus 70. Here we are, resting membrane potential. But then this neuron released its neurotransmitter. Sodium came into the dendrites and cell body. And so cumulatively enough, it made it where we're no longer minus 70 in this environment, and we've actually reached this threshold point. So we've reached this threshold point, and it is at this threshold point, I'm going to put an X here, that now we have opened the first voltage gated channel on the axon and caused sodium to massively influx into that area. So this whole time we've been measuring from the start of this axon. From the perspective of the axon right here, it says, hey, we're hanging out at minus 70, minus 70. All of a sudden, something happened. We know now it's from another neuron. We're getting more and more positive in the area right adjacent to me. So it's feeling of a more positive environment because the sodium that had come into the cell body, that finally it triggered the opening of these sodium voltage gated channels that caused a massive influx of sodium there. So at this point, we will say, I'm going to abbreviate it as Na+. I usually write voltage as a V with these little caps on there for voltage. Gated channels open. If sodium voltage gated channels open, we know that means sodium influx. Now that's the proper term just to say sodium is going into the cell. And therefore the cell is becoming more positive because we have a positive ion entering the neuron cell. Eventually the voltage gets up, we pass 0, those gates start to close, and it gets completely closed at plus 30 millivolts, where the peak of this rise occurs at. And at plus 30 millivolts, we'll draw an arrow, what happens when we achieve plus 30 millivolts? Yeah, so first we will talk about the sodium voltage gated channels open. Let me put that here, the open to here on the threshold. And then we're going to say they are going to close up here. So we've reached plus 30. The sodium voltage gated channels have closed. They are now locked. We're not going to open them again. It's too positive. It doesn't do us any good to get any more positive. So the cell's like, I'm done. I'm done letting sodium in. I'm super positive right now. I've reached plus 30. At plus 30 is our trigger point for our potassium channels. So at plus 30, so I'm going to erase this stimulating neuron here. So at plus 30, our voltage gated channels will open, and we will then cause the cell to become more negative because now potassium is leaving. So now we have a positive ion escaping out of the cell. So then because a positive is leaving, it's becoming less positive or coming towards the negative. So that is due to potassium, and the term for this is potassium efflux, like it's exiting the cell. So you can see sodium influx or potassium efflux. Plus 30 opened the potassium voltage gated channels. And because the channels were open, it allowed for potassium to then leave the cell. And the term for that is efflux. Because it tells you that it's moving, potassium's moving, but though I say an efflux with an E, it means it's like escaping versus coming in like it would for sodium. So that's happening. Then we know, and so it's going to open here. So at plus 30 is where our potassium channels are also opening. But then they will, the potassium voltage channels are going to close down here at minus 70. And then we have this loop where we kind of pass minus 70 and we come back up. It is during this time that that pump says, hey, all the sodium that came in during this phase and all the potassium left during this phase, let's get potassium back in and let's kick sodium back out. So we're going to do the exchange. So it's during this time that the sodium potassium pump does its magic and reestablishes the concentration gradient, brings the potassium back into the cell, kicks the sodium back out the cell, and then we have now returned back to our resting membrane potential. So those are the steps of the action potential. I'm going to add a few more terms in here. When we bring the cell to be more positive, it is known as depolarizing. So I'll just write that on this rising phase. So if depolarizing means the cell's getting more positive, what would we call it if the cell's getting more negative? Repolarizing. When we go past resting membrane potential, still in repolarizing mode, but we kind of use minus 70 as our start point. And when we go past it, what is that called? Hyperpolarizing. This phase can be known as an undershoot because it's going under, or an overshoot because it went past. There's a few different definitions for that. Is there any questions so far or something that you need clarified on these? So you know, if I were to ask a test question of a voltage, what voltage would open potassium voltage gated channels? You say plus 30, exactly. What would you say is the primary ion responsible for repolarization? And so the test might say potassium influx. They might say potassium efflux. So not only do you know that potassium is responsible for repolarization, but you have to remember it's potassium leaving the cell rather than coming. So a question like that has, you know, two things. Not only that it's relevant to potassium, but you have to remember which way is it going. Is it going out of the cell or is it coming in the cell to help it recover? And it would be leaving the cell. Yes. Or I may use the efflux as a selection choice, but I wanted to make sure the terms are clear that you know what that meant. The sodium channels and is what we're going to focus on with the locking mechanism. The locking mechanism for sodium channels determines or allows us, the locking mechanism of sodium channels. Remember, we get it closed up here, but it's closed and locked. We don't want to do another action potential too soon before it is recovered. We want to be able to send a signal. Now, everything that happened here, if we want to think of this as one section of the axon, but immediately next to it, we have another sodium channel. And so while this area was going up, getting really positive, it clearly was going to make the environment around its neighbor more positive and cause that one to open, which would then cause its neighbor to become more positive and make that one open. So this is happening progressively as it goes down the axon, and this is known as continuous propagation. we don't want another action potential to be coming along this axon too quickly. We want to be able to let one of these areas reset back to resting membrane potential before another signal comes through. For instance, by the time the action potential gets to the end of the axon, another one could probably make its way down because we've actually reached back down to repolarization and resting membrane potential, that if another neuron stimulated this, we can send another stimulus down to the muscle. So we have what's known as the 2 refractory periods, which is why when sodium channels hit their peak at +30, not only do they close, but they cannot be reopened again, even if another neuron over here makes this area positive. It just says, no, I'm not going to respond. So it's absolute refractory period until it comes right down to -70. Even at this first point that it returns back to -70, we know that our sodium and our potassium are imbalanced. So it's not really quite back to normal yet. So it's only during this phase that now the sodium channel that is closed and locked now goes into sort of locked, where it said the whole time during repolarization, it was absolutely no, it will not open again. But once it gets to -70, it says, okay, but you're going to have to give me a stronger stimulus than reaching the threshold. You're going to have to, go past that to really mean business, and then it will then open. So that's known as relative refractory, like it's recovered but not all the way. So that's just what it is. So the refractory period really is about the sodium channel voltage gated state. One distinction I want to point out, because it differs from what your book shows you on graphs and says in the text, is it counts the absolute refractory period. So I've been really clear that it starts at +30, but it counts it in your book as starting it here from the time it opens, which to me makes no difference because it's open. So why would you worry about it stimulating to open it again? Because it's already open. So refractory is more about when are you going to be able to get the next impulse. So some of the graphs you might see has the duration of the absolute refractory longer just because it's including the time that it's open. But really by definition, it's really more about the locking mechanism. So I just wanted to make that distinction. And that's pretty much everything that we did the last lecture.